Good morning, everybody, and welcome to this session. Today is October 31st. We are in week 9. We have an exam that is next week on Wednesday. Next week, it's about probably 10 days or less. So we have an exam on that day. We have the review that is online. That is really the main focus at this point. The units that we're doing this week are also included in the exam so that you guys know. Units, we did 22 so far, 21, 22, so we're doing 23, 24 are included. Unit 25, which is also this week, is not included. So we have 2 units, which I'm hoping to cover today, and that should be the end of it in terms of contents for this midterm. And you have the review online, so I'm hoping that most of you will be doing the review. The review. Again, the review is graded on its own part. You will get full credit regardless of what you score in it if you take it. If you don't take it, of course, you're not going to get any credit for it. And it helps you to prepare for the midterm. I guess you guys have seen already midterm number 1. Midterm 2 is just follow-up basically in the format as midterm number 1, which will leave us for another exam that is coming down the road after Thanksgiving, of course. And that is going to be the midterm number 3. So, and that is going to include unit 25 and beyond. So these units are all dealing with light up to from 21 up to 25. Actually, 25 I left it a little bit on the side because of the fact that the timing is really, if we include the end of the week, it may not be enough time for you guys to consume it. Furthermore, there are stuff in here. So let me share with you first of all the week so that you see exactly what we have, because we have quite a few things that are due actually that are actually needed this week. Share. Again, these are the objectives, the content, the discussion unit in here. So if I click on it, it's basically talking about the it's not required in a sense. You're not going to be graded for it, but it's a good idea to interject. Again, it's part of the plan in that you don't have you have an exam that is coming down the road. So I want to focus on the exam. So this is not a graded assignment. You see it in the objectives. It's not one of them actually. But these are the units 23, 24, as I was saying, are part of this exam, part of midterm number 2. Unit 25 is not. Okay, it's part of next midterm. There is a link in here that I'm hoping that you guys will take advantage of it, because you have homework 6 in here, but you also homework 5, and you have homework 4, which is from previous weeks actually. Homework 4, and as a matter of fact, homework 4 will be changed, the due date on it. So if you did something wrong with it or you're not happy with its submission, I'm going to change it to a later date, so that you, in light of the video that I posted today for you guys in here in this unit, you will be able to submit it also. Homework 6 and homework 5 are fine in terms of their due dates. They're still coming. And you're not required to submit all of the homework problems. You're only submitting 2 of each. So for a total of 6 problems, basically from each. And the discussion in here is in detail, and you can pick and choose which ones to submit. Okay. Again, this is a link in here. Again, it's a video. It's almost 50 minutes of video, or slightly around that number, that goes in detail about all of the problems from each and every one of them. I know some of the discussions, we did them in lecture, but I wanted to have them all in one place so that you guys can go and look at them. Also, you have a quiz, which is due after the actual midterm, but it should also be able to help you. It's on the units from week 8 and week 7. And the homework, as I was saying in here, and of course, the discussion that we have in here. So the units of focus today are 23 and 24, and we're going to defer the rest for next time. Okay, so let me stop sharing and let me share with you this units immediately so that we have them in. Let me show more videos. Let me find them. Where is unit 23? And here is unit 23. So unit 23 deals with the black body radiation basically and explains what we mean by that in terms of how much materials emit light, basically. Not just light. So when we say emission or absorption, we really mean all kinds of wavelength, not just the visible range. When we talked about the spectrum, if you guys remember, we have a range of spectra. We have the visible, which sits in here, and let's assume that this is the red, and this is the violet. So anywhere between them is the entire spectrum. So on this kind of side in here, you have the UV range, you have the X-ray, and you have the gamma rays. On the other side, you have the infrared, the microwave, and then the radio waves. Okay, and beyond. So when I say emission or absorption, we really don't mean visible light only. All kinds of spectra are acceptable. Okay, the entire spectrum is acceptable. So there is a relationship apparently between, and that is an important concept in here, that the temperature is measured in Kelvin. Okay, so that you guys know, we know at least of three main systems of measuring temperature. The degree Fahrenheit that is used in North America, especially in the United States. Then there is a degree Celsius or centigrade, or this is used in mainly the rest of the world, they use the Celsius system. And then you have the Kelvin. Kelvin is actually a more used for science, okay? So we're gonna be using Kelvin. So that you understand, a degree Celsius is the same temperature in Kelvin. So this is the temperature in degrees Celsius, plus 273. Oh, I'm sorry, the other way around. Plus 273 here. Okay, so whatever you read in degrees Celsius, add to it 273. Okay, so this is in a nutshell what the conversion rate is. Between the degree Fahrenheit and the degree Celsius, there is a formula, 9/5 of whatever the other unit, plus or minus 32. That is to shift the origin, because in degree Fahrenheit, the water freezes at 32 degrees Fahrenheit, but it does the same thing at 0 degrees Celsius. Furthermore, it boils at 212 degrees Fahrenheit, whereas it boils in here at 100 degrees Celsius. So the scale in here is from 0 to 100. So there is 100 divisions in it. The scale in here is from 32 to 212. So there is 180 divisions in it. So it's much finer for the case of the Fahrenheit degrees versus the scale on the centigrade degrees, which is, in other words, for the same degree, for the same change in temperature in degrees Celsius, it's much finer actually. More changes have happened in degree Fahrenheit. That is the difference between them, and the difference is 9/5. In other words, if this is 1 degree Celsius, 1 degree Fahrenheit is about 5/9, slightly more than halfway. So if this is halfway, this would be 1 degree Fahrenheit. So the degree Fahrenheit is finer than the, by about half, basically, than the degree Celsius. That's basically the difference between the two. And the Kelvin scale is actually an absolute system. It starts from 0 Kelvin. You can never have something negative temperature in Kelvin. T can never be negative. It's always greater than or equal to 0. As a matter of fact, there is a law in thermodynamics that even prevents it from being 0. So the degree in Kelvin is always greater than 0. No matter what you do to it, there is no system that can have a negative value. As a matter of fact, you cannot even have a 0 Kelvin period because of a law in thermodynamics. And it can be any high you want to. And the change between a degree to a degree, I mean, between a temperature and a temperature in Kelvin, is the same degree Celsius. It's the same scale as the Celsius degrees. Because the shift actually is independent of the 273, so the shift in degrees Celsius is the same shift at temperature in Kelvin. So this is in a nutshell what we use in science in general, not just in astronomy. We use extensively the Kelvin as a measurement for temperature, not the degree Celsius, not the Fahrenheit. Although, and this is true, you will find in scientific laboratories and publications and even people talking in degrees Celsius. What the understanding is that if you really want to do measurable calculations, don't forget to convert that to Kelvin. Because right now we're sitting at room temperature, and room temperature is about 300 Kelvin. It's much easier to say the room temperature is about 27 degrees Celsius than to say it's 300 Kelvin. So that's really, it's a matter of convenience to communicate that in degrees Celsius rather than in Kelvin. Note too, that you don't call it degree Kelvin, you call it Kelvin, period. Degree, in this case for Fahrenheit or Celsius, but you call it Kelvin as if it's a unit, normal to any other units. That's enough said about the second part. The third part is what I was coming to from here. For measurement of temperature and wavelength, they are inversely proportional to one another. So if I know the wavelength, the maximum wavelength that is, okay, in nanometer. So this is the maximum wavelength. In other words, I have a body that is emitting light, like a light source, okay? Like the sun, like a star, okay? And it's emitting light and it maxes at a certain value. So there is a bunch of values that it's emitting. It's emitting the entire spectrum if you want to. Everything is included. With the exception, it's maximum throughout a certain frequency. For a given wavelength, it's maximum. Remember the wavelength and the frequency are related to through this constant, where c is constant at 300 million meters per second. 300 million, not 300,000, 300,000 kilometers. Anyway, the point being in here, this is Persian law that we discovered way back in 2122, the previous units. So if I say frequency, I mean also wavelength, because this is a fixed number. This doesn't change for all light. So the point being in here is if I know the maximum wavelength in nanometer, it's critical to be in nanometer, then I can measure the temperature in Kelvin. So isn't this great? This is really one of the most powerful laws that you can think of. You have a star that is very, very far away from us, unreachable. If it were not for light, we wouldn't even know that it exists. Emits light. Light takes 300,000 kilometers per second traveling from that light source till it reaches us. Sometimes it takes years to reach us from the nearest star. Sometimes it takes thousands of years, sometimes even millions of years, or even billions of years. It takes a long, long, long time. For these distances between the stars, light as if it's frozen in time. It barely moves because of the tremendous distances. So if you take, for example, Proxima Centauri, which is the closest star from Earth, from the sun, and you send a beam, the beam will take 4.2 years to reach the star. That means if you are one day monitoring that light, let's say, for example, you have a chair, you're looking at the two stars, namely the sun and Proxima on the other side, and then you send a light beam, okay, specific frequency, and you want to track it, and you're looking at it. As you look at it from that distance, light for one day barely has moved. It takes 4 years to reach the other star because of the distances between the stars. And this is the closest star. So light reaches us from there. We take that light, we put it through a spectrometer, device that analyzes different frequencies, and we find where is the maximum intensity from that. Which frequency has more intense, brighter than the others? Which intensity we have more of it than the others? If we find that light, then we measure its wavelength. That wavelength is what is named as lambda max in here. We don't care about the others. We don't care about the ones leading it or behind it. The shorter wavelengths or the longer wavelengths. We don't care about the shorter wavelengths on this side or the longer wavelengths. Whatever that peak is, then we use this formula, and all of a sudden we know the surface temperature of that star without even having to leave our chairs. This is Wien's displacement law, or Wien's displacement law. Now, knowing that, we can take another law, Stefan-Boltzmann law, to find how much that star is emitting of light. What is its output of energy? Its luminosity, which will tell me how much it's emitting. It's proportional to a t to the power 4, meaning this number I have to multiply it by itself, and the result I have to multiply it by itself. I have to multiply this temperature by itself 4 times. Once I find that number, I have to multiply it by a constant 5.67 times 10 to the negative 8. And that gives me how much intrinsic, how much light it's being emitted by that, how much energy is being emitted by that star per second. That means every second it's emitting that light per square meter. Obviously, the size of the star now will matter, okay? If the star is big, it's going to emit a bit more for the same temperature. If the star is small, then it's not going to emit much because it doesn't have a lot of area to emit through. So that is really where the area comes in. And this is every second. So that is the Stefan-Boltzmann law. Okay, I call that Wien or Wien, I think it's a German, so probably it's more appropriate to call it Wien's law. Anyway, so this is basically in a nutshell what this unit is. This is one of the most powerful units there is because of the fact it helps me do a lot. It helps me know the temperature of the star. And if I know the temperature of the star, I know its luminosity. The brightness is related to the luminosity and distance. That is the next connection here. And we will need that down the road because how bright the star is depends on how much light it's emitting every second per square meter and how far it is. Obviously, for a nearby star, this number is very high. The brightness is very high compared to like the sun. The sun is so close from us. It emits what? 4 times 10 to the power 26 watts per square meter. No, 4.6, 4 times 10 to the power 26 watts in general, because we took already the size, we multiplied by the surface area of the sun to get that number. But of course, we are only 150 million kilometers away from it. We are only 1 astronomical unit from it. We are not like 1 light years or 40 light years or something like that away from it. So it basically dominates the day, the night, that dominates the sky, and basically outshines anything. All the stars right now it's 11 a.m. There are stars, actually the same stars that you will see 6 months from today when the sun is actually on the other side of the planet, and this side now becomes nighttime. So the same stars are there. How do we know that? If there is a solar eclipse today, you will see them. But the sun outshines them all, and the sky, you can see nothing of it except the sun. So that's how bright the sun is because it's close. So the distance matters. So again, what do we mean by black body? So this whole now is just an introduction. How do we know all of this? Is by studying a model called the black body. So a black body is an ideal system that emits all light or absorbs all light. So it's an ideal system. The sun is an example of that. You and I are an approximation of a black body. Any object that has temperature, that can emit light or absorb light, if you shed to it, then it's a black body. It can be it can be approximated as an black body. A black body is really an ideal structure. There is no such a thing that 100% emitting or 100% observing. It's always you absorb some and you emit some. So that's really what the nature of all of the materials are. Okay, so it's really an idealization. So when we say that, the laws that we derive, they're based on this ideal system. However, the experiment and observations match a lot. So it's a very, very, very good approximation, I should say. Okay. So this is what the studies have found. Okay. If the temperature is lower, the body emits in longer wavelength for the most part, peaks frequency or wavelength that is longer than when it's a little hotter, and it's longer than when it's even less, far more hotter. So a hotter, you can do this experiment, take a spoon, but don't try this at home unless you are properly insulated. Take a heat-resistant glove or something like that and put it on the stove, put it on the gas basically, and you will see as it starts to, don't do too long because it can melt, okay? So you really have to, you have to be very careful with this one. So the thing with it is, as it absorbs heat, the heat piles up on it, and then its temperature starts to increase. Once the temperature starts to increase, starts to emit light, it becomes a little bit, starts to change color from the metal color until it becomes more like a red color, and then it increases temperature until it becomes white color, in which case all of the spectra are emitted. So the wavelength seems to peak at a longer wavelength with lower temperatures. So it's T is less, lambda is long. That's basically why you have the inverse law in here. And you have a fixed number in there that is coming from experiment or, if you wish, observations. So the light bulb that is 4,000 Kelvin is reddish in color, and its wavelength is 725 nanometers in this case. This is the length of the peak. Light bulb that is 1,000 Kelvin hotter with more temperature in it peaks around 580, somewhere in the region between the transition between red and between yellow and green. Something that is even hotter than that. This is the surface temperature of the sun. Surface temperature of the sun is 5,800 Kelvin, by the way. Okay, so this is slightly hotter than the sun. So it peaks around 483 nanometers. So the wavelength in here is shorter. So the max in here stands for the maximum value. So it's somewhere in here near the bluish color, actually, just below the 500 nanometer wavelength. So this is basically what the studies have shown. I know intuitively you guys have learned always that red is hot and blue is cool. As a matter of fact, it should be the other way around, okay? So blue is hotter than red. That's as simple as that, okay? So in this case, which one is hotter? Obviously, the yellow one is hotter than the red burner because it's emitting even longer, shorter wavelengths than this one. So again, this is a representation of the same. So Wien's displacement law shows me the how the frequency changes or how the wavelength changes with temperature. And actually the Boltzmann law says how much energy is being basically emitted by a source. For the case of a hotter temperatures, this entire area. So there is more area that is inside the curve than if I take it, for example, for less the other one. So the other one is less this area. So the brightness now, or the luminosity now, depends on the temperature, and is actually the temperature to the power 4. So the one I marked with the red is under the curve that is supposed to be 5,000 Kelvin, and the one that I marked in black actually is supposed to be a 6,000 Kelvin. It's a much, much bigger area. Okay, so this is in a nutshell what's going on with the black body radiation. And this is the stuff that has to do with the temperature as it increases, okay? At absolute 0 Kelvin, in this case, temperature is negative 460, negative 273, this is 0 Kelvin. This is the measurements of temperature, as a matter of fact, the one that I was talking with when I started. And as the temperature increases, so there is nothing that can go below this temperature. So this is an absolute minimum. There is no upper limit on temperature, by the way, but we know that there is, at least as far as we know, there is no upper limit. So there may be an upper limit that we don't know of it, but at least this is what we know. There is nothing that can be has less temperature than 0 Kelvin. As a matter of fact, 0 Kelvin itself is an ideal temperature that doesn't exist in real life. Okay, so technically, even 0 Kelvin is not possible. So any temperature above that is fine. And in the lab, we were able to produce very, very, very low temperatures, but not quite zero. Okay, not 0 Kelvin anyway. So and that is negative 273 or negative 460 Fahrenheit. And it's the same temperature, by the way. When you say 77 Kelvin, you merely mean negative or minus 190 degrees, 96 degrees Celsius. So that tells you, if you're familiar with the centigrade system, how cold that temperature is. And if you're not, if you're familiar with the Fahrenheit, it's negative 321 degrees Fahrenheit. Okay, dry ice, which is something that is a common thing that we do in experiments, and now with meat transportation, with the corona and all of that, it's 195 Kelvin, so it's a lot warmer than liquid nitrogen. Liquid nitrogen, and it's a very important thing in here, when we're talking about the planets far away from the sun, this is a potential where this thing could liquefy, and it rains actually on some of those planets. It happens at very low temperature, 77 Kelvin. 195 Kelvin, carbon dioxide actually melts. Carbon dioxide solidifies, I should say. It doesn't melt, it becomes solid. And that is what dry ice is. Okay. Any temperature more than 195, and it goes from solid to gas. It sublimates. Okay. And that is negative 79 degrees Celsius or negative 110 degrees Fahrenheit. At 0 Kelvin, at 0, degrees Celsius or 32 degrees Fahrenheit, it's 273. This is where water freezes. Room temperature is about, I said 293 is very close from that. So 27 degrees Celsius, when you add it to 273, that's 293, okay? Which is about 68 degrees Fahrenheit. The human body is about 310 Kelvin or 37 degrees Celsius or just under 100 degrees Fahrenheit. Water boils at 212 or 100 degrees Celsius, and that is 373 Kelvin. Now, light bulb filament, this is the tungsten, the one that is not the modern one, not the one that uses LED technology or anything like that. This is the incandescent, what do you call it? Incandescent light bulb. Oops, did I jump in here? So that runs about 2000 Kelvin. Okay. And it's about 1727 degrees Celsius. Look, notice when the temperature becomes higher and higher and higher, the degree Fahrenheit, the degree Celsius or the Kelvin, they are matching, whereas the Fahrenheit doubles basically. So that's something that you keep on mind. So the surface temperature of the sun is about 15 million Kelvin or 15 million degrees Celsius. It's the same thing because the difference between them is 273. What's 273 added or subtracted from 15 million? It's nothing. But it doubles in here, in this case, almost doubles for the case of Fahrenheit. So it's 27 million degree Fahrenheit. That's the core of the sun. There are actually much more hotter temperatures than that. Okay, so this is not the hottest temperature. So I talked about this law. This is the Wien displacement law provided. Lambda is in nanometer. Make sure that your lambda is a nanometer, okay? So for example, you and I are around 300 Kelvin. Don't tell me it's not 300 Kelvin, it's 293. Okay, 293. So that's what makes you happy. Sorry. It's 2.9 times 10 to the power 6. So if you want to know what's the max, what's the wavelength we're emitting at from temperature, well, 293 is about 2.9 times 10 to the power 2, canceled with 10 to the power 6. So it's going to be about 1. I mean, you can do the number. It's going to be slightly less than 1, but that's fine. 10 to the power 4 nanometers. So which is 10,000 times 10 to the negative 9. Obviously, 10 to the negative 9 cancels this fourth digit, so I'm going to be left with 10 to the negative 5, actually. 10 to the negative 5 is 0.00001 meter, okay? So that's how long the wavelength is. Or if you wish, cancel another 10 to the negative 5, then, or about 100th of a millimeter. That's the wavelength that we emit at versus, for example, I don't know, 6,000 Kelvin. 6,000 Kelvin now is tremendous temperature, like the sun, for example. The sun is 5,800, which is, so it's 2.9 divided by 5,800. And that is 10 to the power 6. Again, I'm going to take 1, 2, 3 decimal points. And this becomes 3 decimal points. So it's going to be 10 to the power 3. 2.9 divided by 5.8, exactly half. So it's about 1/2 times 10 to the power 3 nanometers. And 1/2 of 10 to the power, that's 500 nanometers. And that's what's smack in the middle of the visible spectrum. Remember, the visible spectrum is between 300 nanometers for the violet and 700 nanometers for the red, and this is 500 nanometers. This is where the sun is. That's why our eyes are sensitive to this range, because of the fact that our eyes are sensitive to what the maximum light that the sun sends. So this will put it right around that bluish color, which is probably a little bit to the green color. That's where the maximum of the sun is, but of course it has more of this side than the other. So when they combine, it gives us white light. So the sun appears white because of all of the maximum frequencies. So if this were the spectrum of the sun, this will be, in this case, the blue, and this will be the red, and most of the radiation is in here somewhere, okay? So that is basically, obviously the spectrum in here is slightly less than 500 nanometer because this temperature is 6,000 Kelvin, slightly more than the temperature of the sun. So it's slightly shorter than the sun. So this is Wien's law, okay? The Stefan-Boltzmann law talks about how much energy is being emitted, okay? How much energy is being emitted. And that energy is proportional to the fourth power of the temperature, T to the power 4 times this constant, which is 5.678. 5.67 times 10 to the negative 8 watts per square meter per Kelvin. I wrote it earlier in joule per second, and joule per second is watts. So it's watts per meter squared per Kelvin, of course, to the power 4, cancel to the power 4, and that's it. So these are the two significant laws that can really, really help us understand the stars and the sun and everything else. This one is a constant divided by lambda max, provided lambda max in nanometers, the temperature is going to be in Kelvin. And the second one is the luminosity, how much brightness the star emits, which is sigma times 10 to the power 4, where sigma is just a constant, in this case, 5.67 times 10 to the negative 8. And the energy is going to be, L is going to be straight in joules per second or watts per square meter, okay? If the temperature is in Kelvin. If the temperature is not in Kelvin, you better convert it, okay? Otherwise, the constant will be different. So the sun, as I was saying, is 5,800 Kelvin, so it's really right smack in the middle of where it needs to be, okay? So this is unit 23. Let me discuss with you guys unit 24. So let me stop sharing and share. Unit 24. Where is unit 24? Here it is. This is 24. Here it is. Okay. So again, we're going to be describing how light interacts with matter, because it's important in here. The entire thing is the following. Light that leaves the sun or any star for that matter doesn't come straight to us. It goes through a region, first of all, immediately above the star itself. And then as it travels, there is an interstellar space that exists between us and the star that could be filled with other stuff, could be filled with gas, for example, interstellar gas. And that gas can absorb some of that light, okay? When it absorbs, the interstellar gas gets excited. It's no longer in the ground state. It's no longer how it's supposed to be. It absorbs energy, then it's going to re-emit it. So in this case, there are two types of spectra that we're going to be analyzing in the laboratory. There's the absorption spectrum, the spectrum where light is actually missing. So we know light is coming from a source and it goes through a material and then it comes to us from the other side. We're expecting the light to be all of it. We're expecting all of the frequencies to be shown, but we will see that there are certain lines missing. Why? Because there is a gas that exists between us and the source, and that gas has absorbed some of that light. So the spectrum called an absorption spectrum, versus a material that you take, for example, and you give it energy of some sort, whether, for example, through heat or through light or through any kind of process. Kinetic energy, for example, whatever any process that you can think of, it gains energy of some sort. Now, it's no longer where it's supposed to be. So the atoms are not in what is known as the ground state. They are excited. They would want to go back to their ground state. They would want to go back to where they were, especially if the agent, the excitant in this case, which is the agent that made them excited, is removed. So in this case, they would want to go back to their ground state. So what they do in this case, they emit light. And they emit light again in specific frequencies. Not all frequencies will be shown, only characteristic of those materials. So in this case, it's an emission spectrum. So usually when we do spectral analysis, either we're dealing with an absorption spectrum or an emission spectrum, okay? So that is really, in a nutshell, what's going on. Now, Kirchhoff's law in this case deals with something very, very important. If you have a source of energy more than what the object is producing, then in this case, the object is actually going to absorb more than when it's emitting. So in this case, it's going to be a net absorber. Now, if the case, the object is hotter than its environment, so it's going to emit more light than when it's receiving from outside. So in this case, it's going to be a net emitter. In the case where the environments are the same temperature, they're the same basically level of energy, then in this case, the object will emit a certain amount of energy and then will receive the same amount of energy. So in this case, it's not an emitter or an absorber, so it's neutral. So this is in a nutshell what this unit is. Now, the thing to remember about this unit is that every single element in the periodic table, has its own unique spectral lines. When it's emitting, it's those same lines that will show up. When it's absorbing, it's the same lines that are missing. So every single element in the periodic table has a unique signature. For the case of hydrogen, it has 4 spectral lines in the visible range, starting from the red all the way to the blue. And those are the spectral lines that will show up no matter what. If you see them with those values, you know hydrogen is present. Helium has its own unique signature. Different than hydrogen, different than any element in the periodic table. Now, if you see those elements, you know for sure there is helium. That's how helium was first discovered. It was discovered when scientists, astronomers started studying the sun, and they discovered this strange gas that has this unique signature in the lines that are coming in the spectral, in the absorption spectrum, because sun is emitting in all ranges, and then there are some that are missing, clearly indicating a gas that does not exist on Earth. That's why they called it helium, the gas of the sun. Helios is the sun. But later on, it was discovered actually it exists on Earth. This is the second most abundant element in the universe after hydrogen. So hydrogen by far is the most dominant element in the universe. Then after that comes helium. Then the rest of the other elements are traces, negligible traces, including ionites, iron, and how much iron the Earth has, and all of the other materials. So this is what you need to know. Now you're saying, okay, what happened to the molecules? Do they have their own unique spectral lines? They do. Except that we really don't talk about the atomic spectra in this case because we're dealing with the molecule by itself. So the molecule can do other things. It can basically vibrate or vibrate or vibrate. So there are different ways of vibrations, that's what I'm trying to say, or spin, or do all kinds of other things. And each and every one of them will correspond to a certain energy that is either absorbed or emitted, depending on how the molecule itself is excited. So again, but usually those are far, far, far more longer wavelengths, less energy to the spectral lines, for example, coming from atomic transitions, which is the focus of this unit in here. Okay. So again, light is, the white light is a combination of different frequencies. So if the source, for example, is emitting light and it comes to us after it goes through a medium, in this case, somewhere, and it comes in here, you run it through a slit, okay? To make sure that you have as small source as possible for that entire beam. Then you run it through either a diffraction grating or a cone, in this case, prism. And in either case, you're going to produce the spectral lines that are making up this light source. Now, here's the problem. It's supposed to be continuous spectrum, but you see some missing lines that start to show. And these missing lines, they differ in, they have, of course, different magnitudes. And those lines, you start counting them. This one corresponds to a specific wavelength. This one corresponds to another wavelength. This one also corresponds to another wavelength. Those values that form are indicative of a given element or combination of more than an element. That is, in a nutshell, what the absorption spectrum is. So in order to understand that, Mr. Bohr basically came up with an explanation for how the atom forms. So before that, there was a problem because the electrons were discovered a long time ago. So we know the electrons are part of the atom. So the atom has a bunch of electrons because they were discovered first, okay? And they were discovered part of the electric current. So people theorized that, of course, matter is not charged. We don't see negative matter everywhere. I mean, this material, whatever that is not charged. I can touch it, it's not discharging, it's not doing anything. So it's neutral. So we know that matter is neutral, therefore there must be an equivalent amount of positive charge to go with the negative charges to cancel it so that matter appears neutral all the time. So the first models that were thrown was like a cookie dough, basically, where you have the dough in here, which is more like the positive charge, more like the entire dough is positive charge. And think of the chocolate chip that forms inside the dough as being the negative charge, okay? So this is negative charges, and the entire dough is positive. So when we do an electric current, or when we do a discharge, for example, by rubbing the material against another one, so what we're doing in this case, we're removing the electrons from one material and putting them in another material, leaving the void as positively charged, the newly one that is negatively charged, and that's basically what the model says. This picture is wrong, though. Why? Because Mr. Rutherford did an experiment. He took foils, basically, of gold and silver and different materials, so he used different materials, and he took those, what is known as alpha particles, that are part of the radiation of some elements, that are fast moving charges, and they are positive charges. So he noted that for the most part, they go unimpeded. So the alpha particles, which are positively charged, they go completely through the material and go from the other end, suggesting that the material is mainly void of charge. Sometimes they deflect, though, indicating that there is a presence of a positive charge, or even reflect, come back completely in the opposite direction, indicating that there is a positive charge. So the picture that emerged from this picture, from this experiment, is that there is a positive nucleus definitely inside the atom, and the charges that are negative are far away from it. And trouble arose immediately. This picture is not stable because of the fact that there is an attraction between a negative charge and positive charge. So this negative charges must fall directly into the positive charge. You say, okay, what happened if they're like planets, for example, the Earth and the Sun are attracting one another, but the Earth is moving fast enough so that it stays in orbit? Well, that's true for the Earth around the Sun, and that's the first model that was described, more like the planetary system. The force of gravity for the case of planets is similar to the force of electricity that is between positive charges and negative charges. So if the electrons are moving fast enough, they should stay in orbit around the nucleus, but that's not correct either. Why? Because of radiation. A positive charge or a negative charge moving, accelerating, will emit light. And these ones are definitely accelerating because they stay in orbit. It's going circularly around the nucleus. So these electrons must radiate energy, and in doing so, they will spiral still down to the nucleus. They don't fall straight out, but they will spiral down. And if you calculate how long it takes for an atom to spiral down for its electrons, you will find it takes no time at all. Before you even blink your eye, the atom becomes neutral again. Basically, there will be no more electrons, and the protons, they will combine again. So that model is a problem, even with the picture that is similar to the solar system. So what Mr. Niels Bohr suggested is, basically, he says, look, what's going on in here is that these electrons, as they go around the nucleus, which is positively charged, this electron must have a wavelength, and that wavelength is a multiple integer of the orbit. So in a sense, it's some sort of a resonance, okay? So it's trying to fall, but it's going on a resonance, so it stays in orbit. That model worked. So Mr. Bohr's model basically gave us a very, very good explanation of how the atom works. So basically you have a nucleus, which is positively charged, a positively charged, I should say, and you have an electron that can exist only at a certain distance, multiples of this number, okay? Half an angstrom, okay, basically. The next level is going to be one multiple than that. The next level is going to be 4 multiples than that, and so on and so forth. Hence this number in here. So this distance is about half a nanometer. Very, very small. So the distance then starts to increase from that point on. So that is basically where and that satisfies this condition that their wavelength, somehow an electron has a wavelength as it orbits, is actually, he didn't talk about wavelength, honestly. He talked about the angular momentum. The angular momentum is a multiple integer of a constant that Mr. Planck has discovered. That same constant that we talked about when we were talking about the energy, which is 6.26 or 6.36, I think 6.26 times 10 to the negative 34 joules per second. So it's that momentum, because that's a unit for momentum too, angular momentum. So there's going to be an integer multiple of that. So he made that assumption, and that assumption he basically just followed basically what Mr. Planck has introduced early on, and he didn't even have a justification for it too, but just Mr. Planck introduced in the context of the black body radiation to explain, to come up with all of those t to the power 4 and lambda max that we discussed earlier today. So again, this works, but there was no explanation for it. Later on, the advent of quantum mechanics that explained these things in here. So that works, and that gives us the different energy levels that is seen in every textbook that you can see. So now the electrons can sit in specific energy levels from 1 to whatever number you have, and they can be excited. Now, if you de-excite the atom, and that's important, this is part of the homework assignments, is that when you de-excite it, the electron can jump only to those specific energy levels, up to the ground state. So if the ground state is n equals to 1, and the atom is sitting at n equals to 3, so the electron can jump back from n equals to 3 to n equals to 1, or can go from n equal to 3 to n equal to 2, and from 2 to 1, or they can go, that's the only transitions in this case. So it could emit 1 photon of a very high frequency, or 2 photons of smaller frequencies each, okay? So this photon will have a shorter wavelength than the other two photons. So basically, that is two possibilities. So every one of these photons will correspond to a certain light. If the distance is big, like this one, the wavelength is actually small and the frequency is high. If the distance is small, then in this case, the wavelength is long. It's not short, it's long, and the frequency is actually less. The relationships that you need to know are this for the energy. So the energy is proportional, so it's h times 10 to the power times the frequency. Or don't forget that we have another relationship between the frequency and the wavelength through this expression. And this is all you need for your homework assignment. Okay, so please make sure you, I mean, I know I posted the discussions, so you guys should be able to go and get them. And hopefully you understand what these things are. So H is 6.26, I think. That's not 6.3. Sorry, 6.26 times 10 to the negative 34 joules second. That's the constant. I may use the 6.36. I think I was off by this thing in here when I was doing the calculations in the homework. So please correct that, okay? Sounds good? Yeah, okay. Make sure you fix this number in the homework assignments. It's not 6.36. It's not 6. Yeah, I think either you do 6.63 or 6.626 if you want to be more specific about it. Okay. So that's constant. That is Planck's constant, by the way. H is Planck's constant. So that's the number I'm talking about from here. It's this H that appears in the energy. So again, the different transitions for the case of the visible light, for example, for hydrogen, they correspond to either less energy, which is the red light, longer wavelength, and higher values of the frequency, or shorter and shorter wavelengths. And those are what you see in the spectral analysis. You will see this light, you will see this light, you will see this light. These are too close from each other. Sometimes they are seeing only one number, or one of them is actually in the ultraviolet region, so you can't see it. So usually you see these lines. And they are all involving as the terminating level as 2. Okay, so if you excite the atom of hydrogen, the hydrogen is supposed to be actually in n equals to 1. So, and then there is n equals to 2, and then is n equals to 3, n equals to 4, n equals to 5, okay? 6. All of the visible spectra that you see are terminating in 2. So what happened to the ones that you don't see? The ones that are terminating in, they're actually in here. They're on this side. They're in the ultraviolet region. What happened to the ones that terminate in 4 or 3? They're actually on this side, okay? They're actually in the infrared. So this is the Lyman lines. So those are the visible. So the others are not visible. So the ones terminating in here, they jump to emit ultraviolet radiations, whereas this one's in here. So this is for the case of helium or the elements in here. So again, if there is a gas in between, this is going to be the continuous spectrum is continuous spectrum. So everything is in it. But the missing lines in here are signature of the cloud, what elements it's made up of. So it has hydrogen gas in here. That hydrogen gas in here will show as these 4 lines that you're seeing missing from your spectra. So this is an absorption line, absorption spectrum. And the difference between an absorption spectrum, which is this one, and the emission spectrum, which is this one, is the lines that are missing in the absorption spectrum are the same lines that are showing in the emission spectrum, versus the entire continuous spectrum. So this one in here, there is no gas between us and that star or that source light or light. Again, this is just the discussion about the emission and absorption. Each and every one of the elements has a unique frequency. So the fact that you have it in here is unique to hydrogen. This one sodium, magnesium, hydrogen. This is also specific for hydrogen. So this two reinforcement of the hydrogen. Calcium in here has these typical frequencies in here, so on and so forth. So when you see that, you can do basically an analysis and find out exactly what makes up that material. So in this case, it's an absorption spectrum because we have the entire spectrum except missing lines. So this is a gas that exists between us and the source. It could be on the surface of the star for all we care. Okay. And this analysis suggested the composition of the sun that is mainly hydrogen and helium. The rest, which is carbon, less than 1%, oxygen, which is less than 1%, and traces of neon also in the atmosphere, nitrogen also in the atmosphere of the star, and iron, actually in the atmosphere of silicon, which is also in the atmosphere, and gold, which is 1.410 to the -8, uranium even less than that. So again, this is based on the spectral analysis and how much energy is being removed from the star. So this is the discussion for this unit. I mean, this is actually the entire unit, and this is the two units, the 23 and 24. Those are part of the exam, which is due next week. And the review, you guys have it on Canvas. Don't forget, you have your final observations for the lunar project also. And don't forget that you have to conduct those observations and submit them. And you have a lot of other assignments to take care of. For the homework assignments, I posted a video. So hopefully you guys will take care of that too. Thank you. I'm going to change the date or the due date on homework 4 so that it's actually the same date when homework 5 is. Thank you, guys. Okay, let me first of all end the recording and then exit.